So today let's start chapter number 4 for NET Physics, which is of work and energy. So let's start first with the definition for work. I'll give you a scientific definition, although the term work is used in everyday daily life, right? As you're performing any kind of mental or a physical activity is you use the word work for it. But that's not the scientific definition for work. So what is the scientific definition of work? So scientifically, if you have a force which will move or displace a body, or it stops a body that is already moving through a certain distance, then work is done by this force on that body, right? So suppose that this is the body that we're talking about, and I apply this force in this direction, and the body moves in this direction, and let's say that the angle between the direction the body moves, or the distance that the body moves, and the force that I applied is some angle theta, then the work done on this body by this force F is defined as the dot product between the force that I applied and the distance that the body moves, right? So remember that the dot product will always give you the components where both F and D are the same, right? So the direction of F and D is the same. So which means that this dot product is defined as FD cos of theta, where again theta is this angle. Now because I have this angle theta in my expression, then I can discuss some of the cases that are dependent on this angle theta. So now suppose that this is the normal to this block, right? And our angle is less than 90 degrees. What that means is that this angle between force and D, it is not going to cross this normal. And if that's the case, then you think about it in this way, that the force is always going to be in the direction where you have the distance, right? So you're moving the body to the right, and the force is also along that direction. So it's acting to move the body to the right, right? So what you're doing is the body is moving to the right, and the force that is being applied is also in favor to move this body to right. And hence, in that case, the work done would be positive, right? So it would be greater than 0. So the next case is if the angle between your force and this distance is exactly equal to 90 degree. In that case, this force would be pointing in this direction towards the normal, right? So it would be the vector would be placed on this normal, and in that case, think about it, the force is neither in favor of moving in this direction where we have D vector, nor is it opposing. So it's neither in this direction, right? It's not in this direction. It's not opposing this motion, which is causing it to move in this right direction, right? So in that case, there will be no work done by this force F on this block, right? So the work done would be 0. Next, we have theta is greater than 90 degrees. And so if I come back to this figure, think about it, the angle, if it is greater than 90 degrees, then it would cross this normal and move to the left, right? So the force would be in this direction, right? In this, let's call it left quadrant or whatever. So it would be in this direction. And the distance D is still pointing in this direction. And so the force is opposing the direction which we want the block to move, right? And so in that case, the work that is done by the force on this block would be negative, right? So it would be less than 0. So you can think of an example for a force that does negative work. If you think about this figure and the explanation that the force would be acting in this direction while your motion is along this direction. What is that type of force? Well, of course, it's friction force, right? So friction force opposes the direction of motion, and hence the work done for a friction force is always negative, right? So what would be the SI unit for work? Think of it in terms of force and distance, right? So here are the SI units for a force. We have newtons, or it's also measured in kilograms meters per second squared, right? And this unit, it is named after Isaac Newton, which is this N Newton, right? And distance is measured, the SI units for distance is meters. Hence, the units for work done would be kilograms meters squared per second squared, or it would be Newton meters. Now, you can define another unit, or let's just say you can give this unit, SI unit, these units, you can give them a name, and that name is joule, right? So you represent that with J, capital J. And of course, work done is a scalar quantity as it comes from the scalar product of F and D, right? So this dot product is also called a scalar product, which will get rid of the directions, right? So unit vectors are eliminated from this because of this dot product, right? So what about the area under a graph which is force versus distance graph? So here is an example of a force versus distance graph, and this is your function force as a function of distance, right? Okay, so what about the area under this? So the area would be the area of a square, right, which is side multiplied by side. Or if you could also think in terms of, well, this is just an example, right? So what if it was a rectangle? So then you would have area of a rectangle, which would be length into its width. And so what do you get when you multiply this? Suppose that you have some F over here and some D over here. Well, you get F times D, but what was F times D? It is simply the work done by the force F in moving the object some distance D, right? So if you look at the graph carefully, then you see that the force is constant along all this region, right? So this means that the work done given by this area is also called the work done by a constant force, right? So the work, if your force is constant, then the work done is simply defined as this F dot D. Now let's suppose that you have a graph that looks something like this for a force versus displacement or distance. Then it's a curve, you see, right? It's a curve, which means that at this point there is some force, but at this point there is some other force, right? Or I should see it from this axis. So you see at this distance, this is there, the force is this. Then you see at this distance, the force has some other value, right? So it's going down. So which means that the force is, of course, variable. So what do I do now? Well, what you can do is you can divide this curve into multiple parts as something like this, right? So you see that so let's say we have these lines that I have drawn over here. We have divided our curve into I parts, right? And hence even though in this drawing it may not look that all these dividers are equal in length, well, they are equal in length, right? So we have I and they're all equally placed, these lines. And so for every line, the distance between these two lines is some delta di, right? So this I is a subscript which represents, this is for I equals 1, 2, 3, 4, 5, 6 and so on, right? So we have I is the number of lines that I have over here, Perfect. So what would be the work done now in this case? Think about it. Of course, it would be the area under this curve. And how can I approximate the area under this curve? We use our knowledge of limits, right? And so the area under this curve is given by a limit, which we say that we'll decrease this distance to almost zero. So we're taking a limit as delta d goes to 0, and we'll sum over all of these areas, right? So it would be something like fi cos theta I, right? And delta di, which is this distance, right? And so this would give you the work done by this force, which is a variable force. Hence, a work done that is calculated in this manner, right, it is known as work done by a variable force. Now let's talk about fields, specifically a conservative field. So let's see what does it mean by conservative field, right? So a field is said to be conservative if it satisfies two conditions. So what are those two conditions? So first we have that the work done along a closed path should be equal to 0, right? Which means that the closed integral, mathematically, we can write it like this, the closed integral of f dot d should vanish. So this circle that I have on this symbol of integral, it just means that the integral where the path that I'm taking this integral on is a closed path, which means that the path's starting point and end point are exactly at the same location. So maybe this is the path, right? And you can see that the start point is A, and it moves along this line and it comes back to the same point A, but I denoted it with B. So saying that A is the path, a point of start, and B is the end point, right, for this path. So this path is closed. Now, if the work done along this closed path is 0, then the field for this path, it is conservative field. And the second condition is that the work done that is independent of the path which is followed by your body, but it depends on the initial and the final position of the body, right? So it depends on the starting and the end points of that path. And in this case, when these two conditions are satisfied together, right, then the field is known as a conservative field. Some of the examples are, well, we know that the gravitational force and electric force comes from these gravitational and electric fields, right? But it turns out that these two fields, they satisfy these two conditions, and hence they are known as conservative fields, or gravitational or electric forces are conservative forces. With this, think about a force that is not conservative. Friction force is a non-conservative force, right? And let me give you a very neat example for this. So suppose that over here I have this black mark, right? And now to erase this mark, you would use a rubber or an eraser, right? And what you would do is you would erase, let's say you start from this point, right? And you end at this point. So I erase something like this, right? So it's something like this. Now think about this. Your starting point was this point A, and your end point was B. Now, you see, this is the pattern that I have erased from this diagram. What if I do the same thing, and let's say now let's repeat this thing. Let's say this is point A and this is point B. If I only erase a start point, right, which is, let's say, this, and then I erase the end point, which is, let's say, this, is this result same as this result? Obviously it's not, right? And hence I have done more work when I erased from A to B. I followed this path rather than just erasing from initial start point and end point, right? And hence this means that my work done was not independent of the path that I followed to erase from this A to B when compared to when I erased from this A start point and I erased at this end point. So the result is not same at all, right? And hence friction force is a non-conservative force, right? So there was a friction when I was erasing it, right? So when you erase something, friction is responsible for that. You can think about this. Just take a piece of paper, write something on it with a pencil, and then try erasing it with an eraser, right? So it's the friction that's causing the erasure of whatever you wrote with the pencil. So I hope that this example made things clear for why friction is a non-conservative force, right? Now, do you ever think about what is potential energy? Why do we have potential energy? Well, you know, kinetic energy is pretty understandable, right? It's pretty straightforward. Something is moving, it would have some velocity, and the energy associated with that velocity is the kinetic energy. But what about potential energy? The conservative forces and fields give you an idea about this potential energy. Well, what happens is that a conservative field or force, it has a property, and that property is that it stores energy in your system. And then this energy which was stored due to conservative field or a force is known as the potential energy of that system. So that's the reason when I say that I raise something from a ground level, there is some gravitational field in that place, right? And so when you're raising something, what you're doing is you're giving that thing, whatever object that you raise, it will store some energy, and that energy is called the potential energy of the system. And the conservative forces and non-conservative forces, they are exact opposite of each other. So the work done by a conservative force for a closed path is 0, but the work done for a non-conservative force for a closed path will not be equal to 0, and so on, right? So whatever you have for conservative forces, the opposite of that is a non-conservative force, definition wise, right? Now let's move on to the topic of power, right? So what is power? So it is, in very simple terms, it is defined as the time rate of performing some work, right? So it is how fast can I move something or stop something, right? So that is what is power. So suppose you have a linear motion where, example, consider this block, and you apply a force and move it some distance d in this linear direction, right? In that case, the power is given by this expression over here. So we have force times distance, which is work, divided by time. But what is d over t? We know that that is simply velocity, and hence you get an expression for power, which is force times velocity. So it's the dot product of these two vectors. Next, suppose that I am performing some rotational motion. So for example, just consider this, that this is a rod and attached to it is some ball bearing or a ball, and it's the distance from the rod to this ball is position vector r, and you're applying some force to basically rotate this ball around this axis of rod, right? And it's going to rotate with some angular velocity omega. In that particular scenario, the equivalent of this force is just your torque, right? So in this case, then the power is given by the dot product of these two vectors. One is the torque and the other one is the angular velocity. And now consider if you were to compute an average power, and that would be given by this P with these brackets around it, right? And this is given by the average amount of work which is done in a particular time, right? Which is just the average force that I would need to basically move my objects from distance d in a given time t. So the average power is given by this expression over here. While the instantaneous power is given by a limit where delta t goes to approximately, or let's say delta t is going to 0, right? It is defined as the ratio of change in the work done divided by change in time. And then you can convert, now this thing can be written as a derivative, as a time derivative of work done. Sometimes you would also see something like this where you have a dot on top of a quantity. That just means that this dot is representing this time derivative, d over dt, right? D over dt is represented with this dot. So it's just another representation of writing your derivatives. Not just any derivatives, specifically a time derivative is written with this dot. So the units for power are written as the units of work done over units of time, but we know the units for work done is joules, right? And units for time is seconds. So it is joules per second, and you can give it a name for this, which is known as watt. So you can say that power is represented in units of joules per second, or it is represented in watts. Sometimes you would see this unit for power, which is horsepower. And in very ancient times, the engines were used in replacing horses, right? So at that time, it seemed convenient to just, it was basically how many horses would you need to produce this amount of power by an engine, right? So it was just back of the paper math, right? But now it's very common. It's especially used in vehicles. You measure their power using this unit of horsepower. And so 1 horsepower is simply 746 watts, or it is 550 foot-pound per seconds. Moving on, let's talk about something that's called the work energy principle. So the work energy principle, it simply states that the work that is done on the body, it is equal to its change in kinetic energy, right? So what's physically happening in this expression over here is that you're performing some work on a body, and that work is basically changing the velocity of that system. Now, it could either increase the velocity or it could decrease the velocity of your body. And hence, the kinetic energy of your system is being changed. Now, if the velocity which is being changed, if the velocity increases, then the work is done in the favor. If initially what your goal was to increase the velocity of that object, but if you wanted to increase the velocity, but the work is done to basically decrease that velocity, then the work done is negative, right? So you get the point, right? Right. So, but what is energy, right? So in very simple terms, I can tell you that energy is the ability of a system or a body to perform work, and this ability is defined as energy of the system, right? So we have discussed work in terms of moving something, right? But you can think of an example where you have a system that is connected, or a block or a box that is connected by a spring, and it's oscillating back and forth, which is known as a spring system. You can call it a spring system. And we can now discuss what would happen for a spring, so in terms of work done. So what would be the work done by a spring? So consider this system. It's a spring and a ball is attached to the spring, and at this point it's about its mean position. What if I pull this to this side, right, in this direction of x? So there would be a force on this ball, and that force is minus some k times x, where this k is just a proportionality constant, but it turns out that this constant, it is the spring constant. So this k depends on the nature of your spring. And so you see this, there is a negative sign, and this negative sign just is basically physically telling you that when I pull this ball in front, right, what is happening is there would be a force acting on this ball which would want to make this ball move to the left, and hence this negative sign. So here is what happens. I pull the ball to the right some distance x, and then I'll release it, and naturally it would want to go back to its mean position, so it will start oscillating and then come back in this position, right? So what is the work that is done in this case? So suppose that when the ball is returning back to its mean position, in that scenario the spring is going to perform the work, and the work done would be given by this expression, which is half kx squared. You can work this out yourself. It would be a nice exercise, recalling the graphical representation which I gave you as a force versus distance graph, right? So you can use this force and you can work out the area of that graph, and you can see if it comes out to be this thing over here. Now suppose instead of this thing that it's you pull it and it's coming back to its mean position, what if the ball that I attached was what this ball does is it compresses the spring, so it makes this length of the spring shorter. In that case, spring force is going to perform the work, and the work done in that case would be given by this expression over here, and you can see the difference between these two is just this negative sign, and this negative sign is telling you that the object that I attached to the spring, that object is compressing the spring, right? Now let's talk about efficiency. So whatever we have talked about now, it allows us to define something that is called the efficiency of your system. And it is defined, efficiency is defined as this thing over here. So before I tell you, let me just tell you that efficiency is represented with this symbol eta sometimes, right? Normally you can just write efficiency, or you can use the symbol eta. So what is efficiency? Efficiency is basically the ratio of the required form of energy that is obtained from your system as an output, right? And it is the ratio to the total energy that you give it as an input. So it is the total input energy, right? So from this, if I just multiply this thing by 100, right, what I would get is the percentage efficiency of the system. And hence the percentage efficiency is given by this thing times 100. Note that efficiency is unitless, right? And the reason for that is in this ratio, both of these quantities have the units of energy, and those would cancel out, and this 100, it has no units. So there is no units for efficiency. It's a unitless quantity. So a machine or a system is said to be an ideal system if you have its output form of energy or work is equal to the input energy that I give it, right? But this is just a hypothetical machine. In practical, there is no such machine really that would give you this thing, right? But here I'd like to leave you with an example. Think of a heater, right? So you have a heater, and its job is to basically heat the environment, right? And so what is happening is you're giving it some energy, and it is converting that energy into heat energy. So is that not 100% efficient? Is that not an ideal machine? So I leave you with this. Think about this, and leave your answers or your thoughts in the comments below. Now, moving on, let's quickly talk about gravitational potential energy. So, the absolute gravitational potential energy of any body on the surface of the Earth is given by this expression over here, where this is the gravitational potential energy, and G is the universal constant of gravity. We have capital M, and this capital M is the source mass, so it could be the mass of the Earth, right? And M is the test mass, so it is whatever mass that you're, for example, raising and giving it some energy, which is the potential energy, and R is the distance from the of your test mass from the source mass, right? And you see that there's a negative sign over here, and this negative sign is simply because of selecting zero reference level of potential energy at infinite distance from the Earth. So that's what we do, right? So we say that the potential energy is zero when the distance from the Earth or this source mass is infinite. Now let's quickly relate the kinetic energy of a system to the momentum of that system. We have talked about momentum in previous chapters, so let's see how this works out, right? So everyone is familiar with this expression for the kinetic energy of a system: half times mass times the squared of velocity. And we also know a relationship of momentum, which is mass times velocity. So you can think of relating P and Ke, so the momentum and kinetic energy can be related if you look at these expressions. So what if I were to break this expression for kinetic energy in this way, right? So I have half mv and v. So these two v would combine again to give you v squared. So this is completely okay. Now, what is mv? Mv is simply p, which I can write it like this, right? Half times pv, and then you can also write this down in this form, which is p squared over 2m. So now let's just quickly talk about escape velocity, which is related to the gravitational potential energy. And the escape velocity, it is basically defined as the minimum initial velocity that is provided to an object which is on the surface of the Earth to escape the surface of the Earth. Basically what it's doing is it's escaping the Earth's gravitational field, right? And the expression for escape velocity is given as this thing over here. So the escape velocity is the square root of 2g mass of the Earth over the radius of whatever object that you're trying to make it escape from the Earth, right? So this is the radius of the Earth from its core to its surface, right? And then you can write it in terms of the acceleration of gravity due to gravity, which is ge. So on Earth it's about 9.81, right? And so you can write the escape velocity in this way. How do we come to this expression for the escape velocity? Well, now think about this. So the object that you're trying to make it escape the surface of the Earth, the gravitational field of the Earth, basically, I think this surface of the Earth, by surface of the Earth, I don't mean that just you're jumping and you're escaping the surface of the Earth for some time. Basically, I think I should change my wordings over here and say gravity of the Earth, right? So I was talking about this thing where I say, how do we come to this expression, right? So you want something to escape Earth's velocity. Now, to escape the velocity, not velocity, I mean the gravity of the Earth, right? So to escape the gravity of the Earth, it has to basically escape the gravitational potential energy of the earth, right? So it has to overcome that energy. So you have to give this object some amount of kinetic energy, and that kinetic energy should be at least equal to the gravitational potential energy of the earth, right? So mathematically, this just means this thing where this is the kinetic energy of the object that I'm throwing so that it escapes the field of the earth, and this is the potential energy of the earth itself. So the kinetic energy should be at least equal to this energy, right? And so then you can solve it for V. So V squared is equal to this thing, and then you just take the square root on both sides, so you get this expression over here, and then you add subscript es, or escape, to V, because now that's the escape velocity that it would need. That's the minimum velocity that you would need to provide this object for it to escape this gravity of the earth. So one thing that you note in this expression over here is that the escape velocity does not depend on the mass of the object that you're trying to throw away, right? That you are trying to make it escape the gravity of Earth. So it's independent of that mass. So it doesn't matter if how heavy that mass is, as long as it attains this velocity, then it can escape the field of the Earth. And now typically the value for the escape velocity, because you see that these are all constants, this is g is a constant, we can plug its value in, we know the mass of the earth and we know the radius of the earth, so just putting in these values and square rooting this expression, you can find the escape velocity, that is, you need to give it to an object to escape earth, is about 11.2 kilometers per second, right? Now, let's talk about one of the very important principles or the conservation laws in physics. All of the conservation laws are extremely important to physics, right? And so we have this one, which is the conservation of energy, right? We have talked about conservation of momentum, if you remember, in previous chapters. So let's talk about conservation of energy. So the conservation of energy is just saying that the total energy of a system will always be a fixed constant, right? So the energies in there, they change their form, right? They could change their form. They may be transformed from one of the forms to another form, but you cannot create or destroy energy, right? So this is the law of conservation of energy, and this conservation of energy cannot be violated, right? So this is very important in physics whenever you're doing things. If something is violating conservation of energy, then there has to be some problem with that thing, right? So it's a very basic principle of physics, right? So yeah. Okay, so to illustrate this, just consider this example where I have a ball and it's raised to some height h from the ground surface, and then you release it and it's going to fall to the ground, right? So what happens over here, if you neglect the losses such as friction and all of those things, then we say that well, of course, when you raised it to some height, you have in the gravitational field because gravitational field is conservative, then that has stored some energy in this ball, which is the potential energy, and that is given by mgh. Now, this energy should be entirely converted into the kinetic energy of this ball as soon as I release it from this point, right? And so as soon as I release it, it will start moving with some velocity, and then I can say that when it hits the ground, when it's coming to this point, right? So I'm releasing it with some initial velocity. Let's say that you're releasing it, so the initial velocity is 0, but it's going to hit the ground with some velocity, and so the entire potential energy has been converted to kinetic energy of this ball, right? So from here you can find the value of velocity with which it's going to exactly hit the ground. Just before it hits the ground, then the velocity is simply given by this expression over here, right? So I've just solved this thing for v. So this is the velocity of the ball when it is just about to hit the ground. And so with this, then we conclude the chapter number 4 of work and energy for